Hello and welcome back to our series on mathematical proofs. Today we're going to be doing proof by contradiction. And it's a rather simple idea, right? We're starting with a claim that we'd like to prove. The example I'll do later is square root of 2 is irrational, right? But it could work on lots of different claims. The basic idea is we want to assume the negation of the claim. Okay, so we have to figure out what the negation of our claim is, whatever claim you're trying to prove, and then we assume that it's true. Okay, we assume the negation is true. Then the next step is that we show that our assumption that we made leads to a contradiction. And this is really what makes the proof work, because you can't have a contradiction, right? Basically, you can't have a situation where you have some statement that's true and false at the same time, right? If your assumption implies a contradiction like that, then you know the assumption we made is wrong, right? So essentially, we're proving the negation of the statement wrong by showing it leads to a contradiction. Therefore, we can conclude that the original claim is true, right? If the negation is false, then the original claim must be true. Okay, so let's take a look at how we would do this with a specific example here. So you've probably heard before that the square root of 2 is irrational. You probably learned this way back in high school. And we want to notice that irrational means a number can't be written as a ratio of integers. And to prove this, we have to show that there are no integers that we can pick, right? This will never work. We can never write the square root of 2 as a ratio of integers. Okay. To do this, we're going to do a proof by contradiction, right? Okay, so step 1, right? We want to assume the negation of this statement. Well, by definition, right, the negation of irrationality is rationality, right? So the negation of this statement is square root of 2 is rational, right? So we are going to assume square root of 2 is rational, right? In other words, we're assuming that there exists an a and b, which are both integers. So there exists these integers a and b such that the square root of 2 is equal to a over b, okay? And furthermore, any fraction of integers can always be reduced in such a way that at least one of the numerator or the denominator is odd, okay? So where at least one of a or b are odd, right? So they could both be odd, but we know that there's a way to reduce the fraction such that at least one of them are, right? Okay. Now, this fact here that at least one of these is going to be odd, this is how we're going to create our contradiction, right? So we've assumed this is true. Now what I'm going to do is I'm just going to do a little bit of algebraic manipulation. Multiplying both sides by b, we get the square root times b equals a. Okay, nothing crazy there, right? So And then I'm just going to square both sides. So then I'll get 2b squared equals a squared. Okay, so since a squared is written as 2 times b squared, right, a squared must be even, right? Because that's really just what it means to be an even integer. It means it can be written as 2 times something, right? 2 will go into a squared evenly here. Okay, so thus a squared is even. Now perhaps you remember from from some classes where you may have done stuff with even or odd numbers. If you square an odd number, you're going to get an odd number. Okay, so therefore, since a squared is even, a cannot be odd. A must be even as well. Right, so okay, so we have a is even, and remember we said before, we can write root 2 as a ratio of integers where, when they're reduced, right, this is the reduced fraction, at least one of a or b are odd. Well, since we showed a is even, that means b must be odd, right? Okay, so, well, I'll just write therefore, this symbol means therefore. Therefore, b is odd. Okay, so b must be odd. Now, the next thing that I'm going to do, because I haven't reached a contradiction yet, right? Everything is fine so far. But what I'm going to do next is I'm going to do a little bit more manipulation with this stuff. Okay, so a is an even number. Since a is even, I'm going to write a as 2 times some other integer m, let's call it, right? Okay, for some m in the integers, right? So a can be written as 2 times some other integer because it's even, right? 2 goes into a evenly. Then 2b squared is equal to a squared, right? That's just from here. We know that's true, which is equal to 2m squared, which equals 4m squared. Okay, and perhaps you can see where this is going. So now 2b squared equals 4m squared. Dividing both sides by 2 will give us b squared equals 2m squared. But this means that b squared must be even, right? Hence, and b squared is even, and by the same logic as before, b is even. And now we have our contradiction, right? Here we concluded that b must be odd, and here we concluded that b must be even, right? This is no good. This is our contradiction, right? This contradiction arose because we assumed root 2 was rational. That's the only assumption we've made this whole time, right? Everything else has just been algebra, normal laws of algebra after this assumption. So therefore, this assumption must be wrong, right? The square root of 2 is not rational. So therefore, by definition, the square root of 2 is irrational. So, when you're writing these proofs, you might write something like, something like contradiction right? B is even and B is odd, right? Therefore, root 2 is, oops, irrational. And that concludes this proof.